This experiment focuses on one of the key concepts in first semester chemistry, and that is balancing chemical equations. You're going to be looking at a number of different reactions between multiple different compounds and determining the different products that can be formed. When you're balancing chemical reactions, you need to make sure that all of the atoms are accounted for, making sure all the hydrogen atoms on the reactant side equal the hydrogen atoms on the product side. All of the sodium atoms on the reactants equal all of the sodium atoms on the products. You're going through and making sure all of these are accounted for when you're balancing an equation. This experiment looks at balancing a number of different equations, making sure the stoichiometry, or the balancing between product and reactant, is correct, as well as identifying what a precipitate, or the solid product of a reaction, would be. This would be based on the solubility of the two possible products. In addition to balancing a full reaction, you're also going to be determining the net ionic reaction, looking at the reaction of just the ions involved in the formation of the solid precipitate. So as you go through this experiment, you're balancing these, you're determining the different ions that are involved, you're identifying the actual product, the solid product in these precipitation reactions, as well as looking at the formation of just that solid product in terms of the net ionic equation. So in this experiment, you're again looking at probably the pinnacle concept of first semester chemistry, and that is the concept of chemical reactions. You're taking elements and compounds and creating something new through chemistry. There are a number of different types of chemical reactions, and in each of these you're starting with some starting material or reactants, undergoing chemistry, and turning them into products. These chemical reactions can be either simple chemical reactions, just taking the elements from the periodic table and combining them into a compound. They could also be a little more complicated, like the reactions in this experiment. You're taking compounds, reacting them with other compounds to make other materials. You're taking multiple reactants, mixing them together, and creating new products. If you move on into more advanced chemistry, there are also many other types of chemistry: oxidation reduction chemistry, acid-base chemistry, electrochemistry. These are all different types of reactions, and they can be multiple different steps involving much larger compounds. In a chemical reaction, you're balancing it. You're looking at writing with the chemical formulas, what are the reactants, what are the products, and balancing them to make sure that the same number of each type of atom, or the same number of atoms of each element, is the same on both the reactant side and the product side. Another thing in a chemical equation or a chemical reaction to pay attention to is the phase. And the phase is the state of matter that that particular compound it is. So there are the three basic states of matter: solid, liquid, gas. You can have a actual solid that retains its shape. You can have a liquid that takes the shape of its container. And then you can have a gas, which is a gas. In a lot of types of chemical reactions,
the different compounds can also be dissolved in a solution. You've looked at solutions before in the lab with different molarities, different concentrations. And these compounds that are in solution break apart into their individual ions. And when you're writing a chemical reaction or a chemical equation, this needs to be indicated somehow. And this is through the phase typically of aqueous. All of these reactions are done using water as the solvent. And so the phase of all of the components that are dissolved would be aqueous. This means that it is broken apart into its ions. So in this example of calcium carbonate reacting with hydrochloric acid, these are the two reactants. Calcium carbonate is a solid, and a solution of hydrochloric acid is used to react. This generates a solution of calcium chloride, carbon dioxide gas, which bubbles away, and some liquid water in its pure form. This would be the balanced chemical equation indicating each one of the phases and all of the varying elements throughout both the reactants and the products. The main type of reaction that this experiment deals with or looks at is double displacement reactions. So in one of these chemical reactions, you have the reactants in the aqueous phase, both of them, and they're breaking apart in the aqueous phase to their individual ions. This example here, a solution, aqueous phase, of silver nitrate and a solution of sodium chloride is mixed together. A solution of silver nitrate has silver ions and nitrate ions. These are separate in the flask or in the container. These are the ions that are floating around with water all in between them. So they're no longer connected to each other. The same is true with sodium chloride. A solution of sodium chloride has sodium and chloride ions separate from each other with water in between, making sure that they stay separated. So when doing a double displacement reaction, you're looking to swap partners. So you can change both, just swap around the cations, the positively charged ions, or the anions. So silver started as silver nitrate. Its counter ion was the nitrate. The end product would be the other anion, silver chloride. The same is true with the sodium ion. You're starting with sodium chloride, but if you switch these around and replace the chloride with the other anion that is in the mixture, you're ending with sodium nitrate. So by swapping these around, you create two completely different products. So the reaction of silver nitrate and sodium chloride produces silver chloride and sodium nitrate. You do have to keep in mind, though, that in this example, these are all one-to-one. Everything switched nicely, but not everything is a one-to-one reaction. If this happened to be calcium chloride, 1 mole of calcium chloride would split into 1 calcium ion, but 2 chloride ions, meaning you would need 2 silver ions to balance that out. And when you have these chemical equations, balancing them becomes critical to make sure that everything is accounted for. You need to make sure that all of the atoms on one side equal all of the atoms on the other. Conservation of mass throughout the chemical equation. So this is a slightly more complicated example of aluminum sulfate reacting with barium chloride. These two components, or these two reactants, are not a one-to-one mixture. So we'll work through this to show you how to go through and prepare these different chemical equations, how to balance them, and kind of go through step by step this whole process. In this experiment, you're not given any of the chemical formulas. You need to determine what is the chemical formula based on the name. So aluminum sulfate has the chemical formula of Al2SO4 taken 3 times. Aluminum has a 3+ charge. Sulfate ion has a 2- charge. So the whole compound is Al2SO4 3 times. Barium chloride, it has the formula BaCl2. Barium ion is a 2+ ion, while the chloride ion is only 1-. So for the compound to exist, there needs to be 2 negatively charged chlorides to balance out the 1 positive 2+ charged barium. So then you have the two separate separate reactants, and they're all in the aqueous phase. So you're splitting them apart into the individual ions, and you need to know how these ions separate apart. Looking at the polyatomic ions like sulfate or nitrate, that these ions are together. The SO4 2- ion is the ion that's moving around in that water solution. This one doesn't break apart because the sulfur and oxygen are bound together using covalent bonds. Also in barium chloride, it's BaCl2, and this means there are 2 separate chloride ions. The barium is the central atom with the 2 chlorine atoms around it. These 2 chlorine atoms are not connected, so it does not break apart as 1 ion of Cl2. Cl2 is molecular chlorine gas, which is not what is in an ionic solid. So once you have all of these separated out, you know which ions you're actually working with, then you're mixing and matching to figure out what are the possible products, or what are the products of this reaction. And by swapping the cations or swapping the anions, you end up with this reaction will give aluminum chloride and barium sulfate as the products of the reaction. So when putting it together in an unbalanced format first, you have aluminum sulfate plus barium chloride as the reactants will give barium sulfate and aluminum chloride as the products. Once you have the unbalanced reaction, kind of the skeleton reaction laid out, you can go through and balance this chemical equation using stoichiometry, or the math of balancing these chemical equations. So to balance a chemical equation, it's best to start with the more complicated compound first. And in an example like this, the aluminum sulfate is the more complicated molecule. There are 5 different ions associated with this one versus only 3 here, 2 here, and 4 here. And they're in a unique ratio. None of them are a 1-to-1 or something like that. This is a 2-to-3 ratio, so it's a little bit more complicated. So you can pick one of these atoms or one of these ions in here to see in the unbalanced format, how is this particular atom looking? And in the unbalanced format, starting with aluminum, there are 2 aluminums on the reactant side and only 1 on the product side. So aluminum is unbalanced. The product containing aluminum is aluminum chloride. And this would need to be doubled in order for the aluminum to be balanced. So you can double the aluminum chloride. So now you have 1 aluminum sulfate plus 1 barium chloride, giving 1 barium sulfate and 2 aluminum chlorides. But when you do this, you have to add whole numbers to the compounds themselves. You can't just add in an additional ion. So this doubled the amount of chloride. So now you can use the next version, use the next atom in this kind of chain. You can take the chlorine atom and see, well, how many are on the reactant side and how many are on the product side. So here you have 2 chlorine atoms on the reactant side and 3 times 2 on the product side, so for a total of 6. This is unbalanced. The reactant side needs to be tripled in order to balance out the product side, so you can triple the amount of barium chloride. Now, 3 times 2 and 2 times 3. There are 6 chlorine atoms on each side of the equation. But this changes the barium. Looking at this equation, there are 3 barium atoms on the reactants and only 1 barium atom in the products. So the barium compound in the product side also needs to be tripled. And this will in turn change the number of sulfate ions. So last one, you're looking at the sulfate ions. There are 3 sulfates contained in the reactants, and now 3 times 1 sulfate contained in the products. The sulfate ion is now balanced. So this here would be the balanced chemical reaction. And you can start over from the beginning, looking at now you have this balanced, will everything work out? Starting with the aluminum, there are 2 aluminums on this side and 2 aluminums on this side, so that checks out. Moving on to the chlorine, there are 6 chlorines on the reactant side, 6 chlorines on the product side, so that checks out. There are 3 bariums in the reactants, 3 bariums on the products, so that checks out. You can do either by ion or by element. If you want it to do by element, there are 3 sulfur ions, 3 different sulfates, each containing 1 sulfur on the reactants, and 3 sulfur atoms on the product, and then 12 oxygens, 4 times 3 on the reactants, and 12 oxygens on the products. All of the different atoms are balanced for this equation. But once you have a balanced chemical reaction, many of these in the experiment have one more step, and that will be the formation of a solid. You will see a solid forming in the observations, and you need to determine what that solid compound actually is. You have 2 possible choices in this, barium sulfate or aluminum chloride. So how would you know which one of these is the actual solid itself? And to choose this, you're going to be looking at the solubility numbers. You've looked at these solubility numbers before in the periodic trends experiment, and you've had to look these up in the limiting reactant experiment. So you're looking up the possible products, looking up the solubilities of these in the Wikipedia table. So in this chemical equation, there are the two reactants and the two products. And these are the numbers at 20 degrees for the solubility of each one of these compounds. You have the aluminum chloride being able to dissolve 48.8 grams in 100 milliliters of water. Aluminum sulfate is able to dissolve 36.4 grams. Barium chloride 35.8, and barium sulfate 0.0002488 grams in 100 milliliters. So to determine what is this solid product, you'll see in this reaction in the observations that it forms a white precipitate or a white powder. What is it? Is it barium sulfate or aluminum chloride? And you can look at the solubility numbers of both of these products. The aluminum chloride is able to dissolve 48.8 grams in 100 milliliters, while the barium sulfate is only able to dissolve 0.0002488 grams, a very, very small amount. So while there is a trace amount of the barium sulfate that's dissolved, anything above this concentration will be a precipitate. It will be a solid that will form. When you're looking to determine what is the solid product, it will be whichever product has the lower solubility number, because this is not able to dissolve as much in the actual solution or in that vial in the container. So once you have the full chemical equation determined, you have the reactants, you have the products, you have the reaction balanced, and you have all of the phases in there. There are two different ways this can go in the equation itself, or in this experiment itself. Some of the reactions are forming solids, while others are not forming anything, and there's not really any reaction. But for those reactions that are forming a solid, you need to determine what is the net ionic equation. So a net ionic equation is determined by first breaking everything apart into its ions. You have the full balanced chemical equation right here, and any of the compounds in the aqueous phase are split apart into their separate ions. So one aluminum sulfate will break apart into 2 aluminum ions and 3 sulfate ions. The 3 barium chloride compounds that are aqueous solution will be split apart into 3 barium ions and 6 chloride ions. Barium sulfate is the solid. This one was identified as the solid based on the solubility numbers. So this one is not broken apart into its ions. So it stays the same. And the aluminum chloride is still aqueous. So this one's also broken apart into its ions. 2 aluminums, 2 aluminum ions, and 6 chloride ions. This equation right here is the full ionic equation. This is every single ion laid out in the products and the reactants. But you'll notice that when you have a chemical equation, you can simplify it. If there are things on this that are the same exact thing on both the reactants and the products, they cancel out. They're not involved in the chemistry itself. They're not doing anything. These would be the spectator ions. So in this case, there are 2 aluminum ions on the reactants and 2 aluminum ions on the products. This is a spectator ion and can cancel out. Likewise, there are 6 chloride ions on the reactants and 6 chloride ions on the products. These are also spectator ions and can cancel out. What you're left with is 3 sulfate ions plus 3 barium ions will produce 3 barium sulfate solid compounds. And you could have, for the net ionic, for the equation, 3 bariums plus 3 sulfate give 3 barium sulfate. But all of those would have the same coefficient out front. They're all 3. The same would be true if you had 2 sulfates plus 2 bariums equal 2 barium sulfates, or 1,000 sulfates plus 1,000 bariums equals 1,000 barium sulfates. The ratio for all of these is 1 to 1. And the net ionic equation is the simplest form of that. 1 barium plus 1 sulfate will give 1 barium sulfate. So when you're going through these equations, you're determining the full balanced chemical equation here. And if a solid is formed, you're also determining what is the net ionic equation for the formation of that solid product. So this experiment is mostly a video experiment. You're looking at a number of different reactions. You're looking at 8 different solutions all mixed together and reacting with each other, and looking at those observations, seeing which ones react and which ones don't. So by going through here and watching that video, you can see which combinations have a reaction and what those observations are, and which ones do not have a reaction. The different solutions that you're going to be mixing together, or that you're going to be seeing mixed together on the video, are aluminum sulfate, barium chloride, lead nitrate, potassium iodide, silver nitrate, sodium carbonate, sodium hydroxide, and zinc chloride. All of these solutions are clear, colorless solutions. But when you're mixing them together and looking at the observations through an array, you'll see that they create a number of different products. Some of them that don't react will remain a clear and colorless liquid, while those that do react, most of them will form a white precipitate or variations of a white precipitate. But there are also some that form different colored precipitates. And by watching this video and looking at these observations, you're recording your observations, and then in the report, writing down the balanced chemical reaction, identifying the products, and looking up the solubility values of those products. And if there is a precipitate, so a solid that is formed from the reaction, you will also be including the net ionic equation. If there's no reaction, you're still balancing the chemical equation, except all of them will be in the aqueous phase. You're still identifying the products and what their solubilities are, but there would be no net ionic reaction for those that do not form a solid. In the experiment, you'll be looking at the observations of a number of different precipitation reactions, or different combinations of different compounds. Many of them will form precipitates, such as in the reaction between lead nitrate and potassium iodide. These two solutions form the bright yellow precipitate that can be seen here. The possible products of the reaction between lead nitrate and potassium iodide would be lead iodide and potassium nitrate. You're swapping the cations, or swapping the anions. To identify which of these possible products is the actual precipitate, you will need to look at the solubility numbers. Lead iodide has a solubility of 0.0756 grams per 100 milliliters of water. The potassium nitrate possible product has a solubility of 31.6 grams per 100 milliliters. With lead iodide having a lower value, this would be considered the precipitate of the reaction, and the potassium nitrate would stay in aqueous phase as its ions in solution. Likewise, you will see a number of combinations that form no precipitate, such as the combination of sodium hydroxide and potassium iodide. This combination still has a balanced equation. However, the products will both be aqueous. In this combination of sodium hydroxide and potassium iodide, the products will be sodium iodide and potassium hydroxide. However, both of them will be aqueous and soluble. If you were to look up, when you look up these two possible products and their solubility values, the sodium iodide product has a solubility of 178 grams per 100 milliliters. The potassium hydroxide possible product has a solubility of 112 grams per 100 milliliters. By looking at these two numbers, there would be potentially a precipitation reaction of potassium hydroxide first before the sodium iodide. However, in these observations, with no precipitate forming, there is no net ionic reaction. So while there will be a balanced reaction and a balanced chemical equation between sodium hydroxide and potassium iodide to give the products of sodium iodide and potassium hydroxide, there would be no net ionic equation because no solid is formed in the reaction. So what was just seen was how you would go about observing some of those reactions, or observing those combinations, both ones that do react and form a solid precipitate and those that do not react. In taking the example from a little bit earlier, the aluminum sulfate and barium chloride, this would be how to fill out the reaction table in the report form. So for aluminum sulfate reacting with barium chloride, you have the full balanced chemical equation, including the phase of each of the compounds. You have the two different products listed. You have the barium sulfate with its solubility and the aluminum chloride with its solubility. And because this reaction forms a solid product, you're giving the net ionic equation. One barium ion reacts with one sulfate ion to give the solid of barium sulfate. There will also be, however, combinations that do not react. So one combination that does not react is aluminum sulfate and silver nitrate. You still are going to be recording and balancing the full balanced chemical equation. In this case, one aluminum sulfate will react with 6 silver nitrates to give 3 silver sulfates and 2 aluminum nitrates. Under the conditions in the video, there was no reaction. There was no solid that was formed. But if you were to look up these solubilities, you'll see that silver sulfate has a solubility of 0.8 grams per 100 milliliters, and aluminum nitrate has a solubility of 192 grams per 100 milliliters. Under the conditions in the video, there was no reaction. However, if the concentrations were increased, most likely silver sulfate would be the first to precipitate. Now, the majority of these compounds and the majority of these products have their solubility values listed on the Wikipedia table, and the link was provided in an earlier slide. But there are some of them that are not specifically listed on that table itself. And these compounds are listed right here. The compound of aluminum carbonate does not actually form. But what happens is aluminum carbonate breaks down into aluminum hydroxide and carbon dioxide gas. The compound aluminum iodide is not exactly, the exact number isn't in the Wikipedia table or some of the other sources that I've tried to find, but you can indicate this as just soluble. Aluminum iodide is a soluble compound. However, at the moment, I'm unsure what the exact number is for the solubility. Silver hydroxide is another compound that does not specifically form, but undergoes a reaction itself. And in that reaction, it forms silver oxide and water. Silver iodide is also not listed directly on that Wikipedia table itself. However, it does have a solubility of 0.0000003 grams per 100 milliliters. So it's not very soluble. Zinc hydroxide is also just like the aluminum iodide. Unsure of the exact number, but you can indicate that it's just slightly soluble. So barely able to dissolve, but most of the time not really. And the last specific thing to point out is for zinc nitrate. While it does, or while this compound is listed on the solubility table in Wikipedia, there's no value for the 20-degree temperature. But you could use the value listed for 30 degrees, and that is 138 grams per 100 milliliters.
The bulk of the experiment is that first part, where you're looking at the observations of all of these different combinations of known compounds. You're looking at the reactions and combinations between lead nitrate, zinc chloride, barium chloride, sodium hydroxide, silver nitrate, aluminum sulfate, sodium carbonate, and potassium iodide. There are 8 different solutions that you're mixing in all of these different combinations to get 54 total mixtures that you're identifying and recording the observations. But each one is a double reaction, or each one is happening twice. So in the case of lead nitrate and potassium iodide that forms this bright yellow solution, you're mixing lead nitrate and potassium iodide in one reaction, and potassium iodide and lead nitrate in another reaction. It's the same reaction, but in the setup and in the array, each combination is listed twice. There are 54 combinations, but only 28 of them are reactions. The second part of the experiment is looking at an unknown. So in the unknown file, you have the observations for those same reactions, those same reaction profiles reacting all 8 of those solutions together. So there are 28 different reactions going on. However, all 8 of the solutions are just listed as 1 through 8. They're not labeled with what they are. You're taking those observations and looking at comparing them to the known reactions to figure out the identity of each of the 8 solutions. The best place to start with that is some of the more obvious reactions, like this reaction between lead nitrate and potassium iodide. This forms a very bright yellow solution. So you can instantly identify wherever that reaction occurs, one of those 2 solutions is lead nitrate and the other is potassium iodide. But you have to figure out which is which. That's where you look at the rest of the pattern of lead nitrate and the pattern of potassium iodide from the known observations. Potassium iodide will only react with one other compound, where the lead nitrate reacts with a few more. So when you identify the first 2, you're separating, let's say, solution number 1 and 2. If solution number 1 only precipitates with one other thing, you know it has to be either lead nitrate or potassium iodide because it forms the yellow solution. And if it only reacts with one other thing, that eliminates the lead nitrate. So you would identify solution number 1 as potassium iodide. And solution number 2, the other solution, would have to be lead nitrate. So you could identify 2 of the 8 solutions just by looking at this one combination and then the radiating patterns. You can then go through and identify, looking at lead nitrate, what are the other precipitations, or what are the other precipitation reactions that happen? What are the reactions, or what are the combinations that do not happen? And you can start to identify and piece together the identity of all 8 of these solutions based purely on the observations and comparing them with the known reactions.
So with all of the known solutions combined, you have the balanced equations, and you've identified the products, the solubilities, the net ionic equations. That is the bulk of this experiment. But the other portion is looking at unknowns. And this portion of the experiment gives you the observations for 8 solutions all mixed together. And they're mixed together just like the 8 known solutions. The 8 solutions in your unknown, listed 1 through 8, are those same compounds from the first part. They're those same known compounds. Aluminum sulfate, barium chloride, lead nitrate, potassium iodide, silver nitrate, sodium carbonate, sodium hydroxide, and zinc chloride. They're all solutions 1 through 8. And your direction in this is to identify what solution matches up with your solution numbers 1 through 8. And to do this, you can think of it like a logic puzzle. You're going to go through and look at these observations stepwise and make some logical deductions. There are a number of different logic puzzles just like this in games, word games. So you have your observations, and the best thing to do is start with the very unique ones first, the ones that are absolutely obvious that you know the 2 compounds that form that observation. And the most obvious one would be the bright yellow precipitate of lead nitrate and potassium iodide. So in this subset right here, I have 3 different solutions reacted just like how you will see them in your unknown files, except you will have 8 solutions. So we have the known observations. Lead nitrate and potassium iodide give a yellow precipitate. Sodium hydroxide and potassium iodide give no precipitate, and lead nitrate and sodium hydroxide give a white precipitate. So these are the observations from the first part, part A. And now you're matching these up with the unknowns. So starting with the most obvious, lead nitrate and potassium iodide, you see that this combination right here forms that bright yellow precipitate, solution number 2 and solution number 3. That means that these 2, solutions 2 and 3, are lead nitrate and potassium iodide. They can't be anything else because only these 2 combinations, or these 2 reactants mixed together, form this bright yellow precipitate. So the other known reactant of sodium hydroxide cannot be solution number 2 or number 3. So now that you know number 2 and number 3 are either lead nitrate or potassium iodide, you need to figure out which one is which. And again, this is looking through like a logic puzzle. Potassium iodide only reacts with one of these components. Lead nitrate reacts with 2 of them. Lead nitrate reacts to form a precipitate with the potassium iodide as well as the sodium hydroxide. So if you look at solution number 2, there is only a precipitate forming that yellow compound. There's no other precipitate. So the silver nitrate cannot be solution number 2 because there's no other precipitate, meaning that solution number 2 must be the potassium iodide. That means solution number 3 should be the lead nitrate, and this can be confirmed with the fact that it does form another precipitate, both the yellow precipitate and an additional white precipitate. So lastly, solution number 1 must be the sodium hydroxide, and you can check this. Does if solution number 1 is sodium hydroxide, it forms no reaction with potassium iodide and a white precipitate with lead nitrate. If you've identified solution number 2 as potassium iodide and solution number 3 as the lead nitrate, you can walk through it. Does sodium hydroxide react with solution number 2? No, it does not, which is consistent with this reaction, sodium hydroxide and potassium iodide. Does it react with solution number 3? Yes, it does, and it forms a white precipitate. And this is also consistent with the reaction of lead nitrate and sodium hydroxide. So now, using kind of those step-by-step logical conclusions and deductions, you can figure out that solution number 1 is sodium hydroxide, solution number 2 is potassium iodide, and solution number 3 is lead nitrate. You're going to be repeating this on the larger scale of 8 solutions as opposed to just 3 to figure out what are the identities of those 8 different solutions.
So the bulk of this experiment, again, is focusing on balancing reactions. You're going to be looking at the observations of 54 different combinations of different chemicals. And in those combinations, there are a total of 28 different reactions that you're going to be balancing. Some of these reactions will form a solid product, and you're going to be identifying that solid product and determining the net ionic equation for that solid product. In the equations that do not form a solid product, you're still going to be balancing what the equation would be, looking at the other products, but they just won't be soluble. So therefore, in a reaction that does not have an actual product, there is still the potential for the reaction to occur, but there's no net ionic equation because no additional product was formed. Everything remained in the aqueous phase. That's the bulk of the report. Look, you can do all of that just by looking at the equations, looking at the compounds being reacted, and determining the different products and the solid and the net ionic equation. The other focus of the experiment is that logic puzzle. You're looking at the observations given in your unknown and then taking those and trying to identify what is the possibility of all 8, or what is the identity of all 8 of those unknown solutions. The different compounds that it could be are all the ones that are normally tested in the initial video. You're looking at matching the pattern of precipitation of the known reactions versus your reactions, observations in your unknown. It's best to start with the very vibrant and distinct reactions, such as that of lead nitrate and potassium iodide forming that bright yellow precipitate, or silver nitrate and sodium hydroxide forming the brown precipitate. From there, you can go through and determine which one is the one compound versus the other, lead nitrate versus potassium iodide, and then mix and match to figure out this logic puzzle of what are those 8 unknown solutions.